Today, the term lab rat is almost synonymous with a laboratory animal. But have you ever wondered why it's specifically the mouse? I know if you search for this question online, you'll get a ton of answers. However, after extensive research, we've found that the bizarre and intertwined history between mice and laboratories is likely stranger than any information currently available on the internet. To understand this, we have to start from the very beginning. Obviously, the concept of a lab animal wasn't always a thing. For a long time, humans have used animals for purposes like setting up traps or practicing surgery before the real thing. But this is a far cry from what we consider animal experimentation today. These animals weren't specifically bred for experiments, and people used whatever was available. If there was a pig nearby, they'd sharpen their knives. If a cow was handy, they'd happily slaughter it. The animal's identity didn't matter. Furthermore, most people feel a natural sense of pity for suffering animals. This is especially true for cultured individuals who are unaccustomed to manual labor. Traditional cultures in many places would associate unnecessary animal suffering with cruelty, evil, or antisocial behavior. In this cultural climate, animal experimentation remained a very primitive practice. All of this began to change in the 14th century with the European Renaissance. It became fashionable to learn about humans and animals directly from their bodies. At the same time, artists needed to understand anatomy to make their paintings and sculptures more realistic and precise. As a result, dissection, once considered a distasteful act, suddenly became a cutting-edge field of study. For example, Andreas Vesalius, the father of modern anatomy, was a 16th-century superstar. His anatomical drawings are still considered a masterpiece today. He would often perform dissections of various animals and human cadavers for high-ranking officials and even royalty. Seeing a top professional mingling with kings, other practitioners were naturally inspired to improve. As a result, dissections and other animal experiments became increasingly public, even resembling a form of performance art to gain more attention. However, the supply chain for human cadavers at the time was questionable. Publicly dissecting human bodies could be risky, as spectators might discover an unfortunate connection to the corpse. There was also the risk of other live show accidents. It is said that during one of his demonstrations, Vesalius was in the middle of his cool performance when a spectator realized the cadaver's cause of death seemed to be the dissection itself. Vesalius was almost burned at the stake for this. These precedents turned human cadavers into a restricted R-rated subject within medical schools. Animal experiments, therefore, came to dominate the field's content. Coincidentally, starting in the 17th century, Europe experienced a massive technological boom. Suddenly, new discoveries in physics and chemistry became popular marvels. Scientists were happy to step outside of academia and give public demonstrations. Sharing their discoveries with the public, animal experimenters felt they had to keep up. Fortunately, technological progress gave them more opportunities for showmanship. For example, in the 17th century, after the chemist Robert Boyle improved the air pump, people began putting small animals into sealed containers and vacuum sealing them to study the effects of air. By the 18th century, suffocating animals with a vacuum had become a standard scientific performance. With this, animal experimentation in continental Europe went into overdrive, sinking further into the public consciousness. After the French Revolution, some radical physiologists and pathologists even began to tie public animal experiments to the concepts of rationality and progress. This led to the most chaotic era of animal experiment performances in history. This all came to a head in 1874. The British Medical Association invited the French physiologist Valentin Magnin to give a talk. Magnin, true to his audacious reputation, brought 2 live dogs and performed an impromptu alcohol intoxication experiment on them. The people of London had never seen such a public spectacle. The sight of 2 dogs being injected with alcohol and left to die from intoxication was met with disgust and outrage. The British public saw this as a barbaric act, a stark contrast to their own civilized methods of quietly experimenting on the bodies of the poor. Shortly after, the UK passed an Animal Cruelty Act that prohibited experiments on dogs, cats, or horses. Surprisingly, France also began to turn against animal experimentation. As science became more established in French society, a group of influential scholars began to argue that animal experimentation was unscientific and that they should be doing human experimentation instead. Between this magical dueling between Britain and France, animal experimentation went from being a single, focused pursuit to a situation where it was being blocked from both ends. What they didn't know was that the wheels of fate had already begun to turn. Just over a decade earlier, a priest in the Austro-Hungarian Empire wrote a letter to a friend, mentioning how delicious his peas were. This priest's name was Gregor Mendel. He is known today as the father of modern genetics, but at the time, all he wanted to do was make his meals a little tastier. This is why some say that having a passion for food is the staircase to human progress. Unfortunately, when Mendel published his classic Laws of Inheritance, which he had derived from his pea breeding experiments in 1865, it received little attention. The letter he wrote to Charles Darwin was even dismissed as junk mail. His work was ignored for nearly half a century. However, his discoveries would revitalize the field of animal experimentation in an unexpected way. In 1900, 3 scientists independently replicated Mendel's results, bringing his laws out of obscurity and ushering in the delayed birth of modern genetics. Naturally, people were eager to know if these laws of inheritance also applied to higher-level organisms like mammals. However, human experimentation was difficult. And even experimenting on cats and dogs, despite the disapproval of the British media, was too time-consuming. This is when an animal that was previously overlooked entered the geneticist's field of vision, the house mouse. As mentioned before, the mouse's survival strategy is to breed rapidly and prolifically. A mouse's gestation period is only 18 to 21 days, and a single litter can easily have more than 10 pups. This large sample size is perfect for data collection. Pups are weaned in under 3 weeks and reach sexual maturity in 6 to 8 weeks. This means a new generation is born in just a few months, so researchers don't have to worry about a delayed graduation. What's more, mice have a unique mating behavior. After male mice mate, their semen hardens to form a vaginal plug that blocks the female's vagina. This ensures that each litter has a single, definitive father, and scientists can easily check for the plug to confirm recent mating. It's as if they were naturally designed for genetic research. To top it all off, at the time, mice were a trendy new pet in Europe and America. The market had already bred many mice with easily observable traits. In fact, the history of domesticating mice might be very long. It's said that in China's Han Dynasty, a pet mouse was bred that would constantly spin in circles due to a genetic defect. After being introduced to Japan and then Europe in modern times, it became known as the Japanese waltzing mouse, so the choice was made. In 1902, the French scholar Lucien Cugnot proved that the inheritance of mouse coat color followed Mendel's laws. This marked the mouse's emergence in the field of experimental animals. This development also had a profound impact on a country with a highly developed breeding industry, the United States. It deeply changed the life path of a young man named Clarence Cook Little. Little's family raised dogs, and when he entered the animal science department at Harvard University, he originally intended to study advanced dog breeding techniques to take over the family business. However, perhaps due to the influence of animal ethics, Little's lab didn't have any dogs. To make matters worse, the Harvard Animal Science Department was so poor at the time that Little's advisor tricked him into becoming the mouse colony manager to avoid having to hire someone else. Embracing the "since I'm already here" spirit, Little diligently worked in the mouse room for several years. During this time, he learned everything he could about mouse husbandry and more. Both he and his mice became famous, and he was known as the Mouse Man. After a while, an idea began to form in his mind. Coming from a dog breeding family, he knew that many dog breeds, such as poodles, golden retrievers, and dachshunds, are all created through many generations of continuous breeding and selection. So Little wondered, what if I apply these same dog breeding methods to mice? Would it work? Sure enough, by focusing on a few specific physical traits, like a certain fur color, and consistently breeding only those mice that fit the criteria while discarding the others, Little created a population of mice with remarkably stable appearance and form in just 4 or 5 generations. Much like a dog breed, the members of this mouse population had very little variation among them. These mouse populations are essentially what we now call a closed colony, but Little wanted to push this further with modern genetics. His idea was this: even in a closed colony, like a dog breed, the genes are not 100% identical. Given the mouse's short breeding cycle, what if he inbred them for many more generations? Could he create a family of mice with almost identical genes? Little's advisor was not impressed. He argued that extensive inbreeding inevitably leads to a decline in health to the point where the animals could not survive or reproduce, a fact supposedly proven by the historical experiments of the Habsburgs. Fortunately, the mouse farm that supplied Harvard's animal department was very meticulous, keeping detailed records of each mouse's lineage. The farm was already trying to breed purebred pet mice, which was only a small step away from Little's idea. Little, who was in charge of the mouse room, decided to go for it. In just over 2 years, by 1911, Little had continuously inbred a pet mouse line called the Silver Mouse for dozens of generations. He successfully created a family of mice with nearly identical genes. They were so genetically similar that they could have organs transplanted between them without any rejection. Moreover, this mouse family showed no severe health problems and could continue to breed indefinitely. This was the birth of the inbred strain, the cornerstone of modern animal experimentation. The first inbred strain in human history, which Little created that year, was DBA. We still use this strain today. Interestingly, Little failed his PhD defense shortly after. It's unclear if his advisor was simply unwilling to accept his research or if he intentionally delayed his graduation to keep him working for another year. A year later, his advisor arranged for a group of old-school academics who opposed inbreeding to turn Little's defense into a public shaming. Little somehow managed to graduate after another year of delay, but Little was incredibly resilient. During that year, he cheerfully continued his mouse work and even got married. With a new family to support, he began to ponder a crucial question: what was the purpose of the inbred mouse strain he had created? It was around this time that he took note of the work of Professor Ernest Edward Tisser at Harvard. Tisser had been studying the relationship between cancer and genetics for years, but as a cancer expert, he didn't have a deep understanding of genetics, which was still a fledgling field at the time. There weren't many people in the world who did. Tisser had spent 4 years trying to figure out why, when he crossbred mice that were prone to cancer with mice that were not, their offspring sometimes developed cancer and sometimes didn't. Statistically, there was no pattern. Little, however, immediately had a strong hypothesis: the symptom of cancer was likely influenced by many genes. Tisser's mice had mixed bloodlines, with a jumble of genes, so the likelihood of developing cancer naturally had no pattern. Little thought, "You're 37 and have hundreds of mice. You should have come across one like mine." He saw that the inbred strain's main advantage was its clean genetics. Combined with his deep knowledge of genetics, his mice were the perfect tool to test his hypothesis. With his new idea, Little smoothly joined Professor Tisser's research team after graduating. 2 years later, they successfully proved that cancer is indeed linked to a large number of genes. This made Little and Tisser the founding fathers of the field of cancer genetics. Crucially, this work also established the fame of the inbred mouse strain. Because their genes were nearly identical, the same procedure would produce almost identical reactions across a group of inbred mice. For example, when induced with the same type and dose of carcinogen, the tumors that grew in different mice from the same inbred strain were almost the same size. This allowed for the creation of perfect control groups in experiments, making it much harder for individual variations to skew the results. Little knew that the more, the merrier. He was generous, openly sharing his mice and his breeding experience. Soon, many others joined in, gradually creating even more inbred mouse strains. In 1920, Little organized an academic summer camp for all American experimental mouse researchers to share resources, exchange experiences, and standardize procedures. Most of the inbred mouse strains we use today were created by the members of these summer camps. This work finally established the inbred mouse strain as a core tool in cancer research. Little then decided to take the next step, to build a large-scale laboratory dedicated to mouse breeding. Meanwhile, venture capital was flowing in. Following the economic boom after World War I, a new class of wealthy people emerged who were passionate about science. As the saying goes, wealth seeks eternal life, so large sums of money poured into cancer research. Little seized this opportunity, and leveraging his status in the field of cancer genetics, he became the chairman and permanent director of the American Cancer Therapy Association. Through this role, Little soon met many American millionaires. These wealthy individuals, while verbally supportive of Little's ideals, would all politely decline when they heard the astronomical cost of building a large laboratory. Just as Little was repeatedly hitting dead ends, a voice suddenly said, "I'll pay for the lab." This wealthy patron was an auto industry magnate named Roscoe B. Jackson. Students and researchers among you might be able to guess what happened next just by hearing that name. Jackson not only provided a generous financial donation but also tirelessly helped Little. Hearing that name, you should be able to guess what happened next. In 1929, Little finally secured the funding and began building his dream breeding laboratory. To honor Jackson's immense contribution, he named it the Jackson Laboratory. But at this pivotal moment, Jackson died for the first time in his life. Although Jackson was gone, his money remained, and the laboratory opened on schedule. However, soon after the lab opened, the Great Depression hit. The lab's wealthy patrons, who had once been so keen on funding research for eternal life, were now busy queuing up on the rooftops. With tens of thousands of mice to feed and the bank account rapidly depleting, Little had to find money, and fast. Looking around the Jackson Laboratory, the only thing they had that could generate income was the mice themselves. The Jackson Laboratory was initially a non-profit organization, and most of its inbred and closed colony mice were shared for free. Little wondered if he could start charging for them to become self-sufficient. But after a quick visit to various research institutions, he realized this idea was a non-starter. Due to his own early advocacy for open sharing, these mouse strains were never patented. Other institutions could breed and give them away for free, so no one would be willing to pay for them. However, during his visits, Little made an unexpected discovery: the experimental procedures at these institutions were incredibly crude. The inbred mice, while seemingly simple, were very complex. Different strains had different constitutions and were prone to different diseases. For example, the C57 mouse strain is particularly susceptible to hair loss, much to the amusement of the PhD students studying them. For more complex experiments, different inbred strains even had to be crossbred to get the most suitable mice. For example, to get offspring that are most sensitive to fertility hormones, you need to cross a 129 male mouse with a C57 female. Furthermore, at that time, the main use for mice in experiments was to study diseases like cancer. You had to induce the disease in the mice according to your research needs, a process known as building a disease model. This was very complicated. Besides choosing the right mouse strain, you had to consider the mouse's age, the method of induction, the drug dosage, and so on. Since inbred mouse strains were a relatively new concept, most labs had no idea how to handle the mice, prompting Tom the cat to shake his head in disapproval. Little's pitch was simple: if the procedures are too complex for you to handle, let me help, and it won't be unreasonable to charge a fee for it. Right, with this strategy, Little saved his life's work. To this day, creating customized disease models for clients remains one of the core businesses of the Jackson Laboratory. To expand his customer base, Little began to research more physiological traits of inbred mice, allowing them to be used for a wider variety of scientific tasks. His years of tireless effort ultimately helped the mouse break out of the field of cancer research and become the undisputed top experimental animal in all of life sciences. As the mouse's popularity grew, that inevitable chorus that every animal researcher has to face resurfaced: "Mice are so cute, why do you have to experiment on them?" This time, Little didn't respond with a direct attack or feign ignorance. Instead, he did something that profoundly changed the field of animal experimentation. In 1935, Little published an article in Scientific American titled "A New Deal for the Mouse." As the title suggests, he was modeling his approach after Roosevelt's New Deal, trying to reason with the public calmly. In the article, he first appealed to people's fear of cancer, then step by step explained that animal experimentation was an irreplaceable part of researching and treating cancer and other deadly diseases. He summarized the medical progress humans had made over the decades based on animal experiments, which had all directly or indirectly extended countless lives. In the final part of his article, he coined a phrase: "Lab mice sacrificed their lives for humanity." The killing is for the sake of protection, not for the sake of killing the mouse. While this wouldn't silence all his critics, it certainly loosened the deep-seated prejudice in society. In 1937, the U.S. formally passed the National Cancer Act, deciding to allocate special funds to support mouse breeding to ensure a continuous supply of controlled, well-understood materials for research. This not only gave the Jackson Laboratory a steady stream of income but also signaled the official stance of the U.S. government. From this point on, the ethics of animal experimentation began to modernize. The general principles of modern animal ethics are: be realistic. At this stage, human scientific research cannot completely abandon animal experiments. Nor can it prevent animals from dying or suffering. Be empathetic. Causing unnecessary suffering to animals is not in line with modern values. Therefore, experiments that cause animal pain must never be displayed publicly. Consider the mental well-being of researchers. The potential mental distress suffered by participants in the experiment should also be a concern. In 1959, two animal researchers summarized these principles into the 3 rupees: replacement. If the research goal can be achieved without using animals, then animals should not be used. If an unconscious or anesthetized animal can be used, a conscious animal should not be. Reduction. To obtain the same amount of data, an experimental design that uses fewer animals should be prioritized. Refinement. Experimental design and techniques should be continuously refined to minimize the pain and suffering of the animals. These are the same 3 principles that are still in use today. Little retired in 1954. It's unknown if he ever went back to his hometown to breed dogs. The Jackson Laboratory was no longer the only game in town. Countries around the world have also established their own large-scale animal breeding platforms. For example, my country began introducing lab mice in the 1920s and was able to independently breed some mouse strains by the 1940s. These included some of the classic white mouse strains we know, such as Kunming White 1, 2, and so on. And since the beginning of the new century, with the explosion of life sciences, the breeding of lab animals has become a discipline so complex that it is beyond your imagination. On the foundation of the uniform genetic background provided by inbred strains, environmental factors must also be strictly standardized. The ultimate result of this philosophy is the SPF, Specific Pathogen-Free, Animal Facility. It's hard to grasp the concept just by talking about it, so we sought help from the Shanghai Experimental Animal Research Center to show you what it's like in person. Before entering the facility, we had to use sticky paper to clean the soles of our shoes and then put on shoe covers. But this only grants access to the public areas on the periphery of the facility. We were not certified to enter the inner part of the SPF facility. Even for passing items in, everything must go through a high-pressure autoclave or a transfer window with multiple layers of sterilization. We could only get a simple look at their breeding area through an observation window. However, I asked the staff to bring out one of their specially designed SPF mouse cages for us to see. As you can see, this mouse cage is completely sealed, and all moving parts have rubber seals. The shelves in the SPF facility are also specially designed with hidden pipes that can individually pump air into and out of each cage. This way, if one mouse gets infected with a pathogen, it's unlikely to spread to other cages. It also prevents the smell of the mice and their droppings from accumulating. Of course, Even the sterile air from the facility's room must first pass through a sterile filter on the cage before the mice can breathe it. Talk about VIP treatment for mice. SPF facilities can only accept mice from other SPF facilities. When they arrive, they must be quarantined in a special room for at least a week. During this time, they undergo a series of microbial tests to verify their health. So, is it possible for a mouse from a normal facility to get into an SPF facility? Only through reincarnation. The procedure, to put it simply, is to take the mouse embryo from the non-SPF mouse and implant it into the uterus of a female mouse inside the SPF facility, ensuring it is born pathogen-free. Of course, this is just a glimpse of the complex standards of an SPF facility. And all of these lab animals are just the tip of the iceberg of today's human scientific research and industrial complex. Next, I plan to delve into more types of lab animals and, through them, give you a small peek into the entire modern scientific and industrial system. I hope this will give you a sense of what kind of industrial Cthulhu human beings have created through hundreds of years of countless attempts, countless rivalries, and countless refinements. See you in the next episode.